to do now is to move on to the introduction. So basically what I'm going to do is just going to go through the chapter 1 of this lecture. We're going to basically follow this textbook. So we're going to go through chapter 1. So that's the introduction of electronic systems. And I've added some discussion on integrated circuit history so that you get a sense as to how they're intertwined together. As I said, if you start by, there are some key technology elements that affects how one studies or make integrated circuits. As I said, when I was in college, okay, we used textbook which mainly focus on discrete devices. We talk about discrete circuits. So when you design a circuit, you basically consider you get a transistor from a discrete transistor with 3 pins, and then you build it up into a amplifier circuits, for example. But nowadays, we don't do circuits in discrete ways. Very rarely, mostly for power circuits. For example, you want to carry on to deliver very, very high power, then you need to use discrete components. But so what happened is that most of the design, I would say 99% of the circuits or microelectronics, we call it microelectronics, is because you're dealing with very, very small and very, very small devices which deal with small signals internally within the integrated circuits. So your design will be mostly for integrated circuit design. So because of that, I want to include some discussion on integrated circuit history. And then we're going to move on to chapter 1 of this lecture, which would touch on some key examples which are very common in your life or in your, you can just have that, you can actually have that module in your phone. Okay, so the electronic system that is in everybody's phone. And then we're going to talk about what are the key elements and how does one analyze these components in the electronic systems, or what are the key modules are critical to this to the success of these type of designs. And then we're going to talk about a little bit as to analog versus digital, even though we're not going to talk too much on digital circuits, but you just to get a sense as to where the roles, where your designs or where these circuits are in electronic systems. And then of course the main, I think the main goal of this circuit, main goal of this class is to allow you to analyze we call it amplifier design. So how does one evaluate a design? How does you rate a design, whether it's a good design? What are the factors one consider as the good performance index? So first of all, the story begins with, I don't know if you ever seen those shows of like in 1900s. So people, like they're announcing the end of World War II. So people are sitting in front of a radio, which is huge. And these radios, they already have these type of amplifying radio signals, electronic signals, without solid-state devices. So how do they make it? Is by the devices on the left. Does anyone know what it is? The devices on the left. Anyone recognize it? You never watch old shows, or like they already had before 1950s. They already have radios. These radios are dealing with electronic signals, and they also deal with. They also have computers for decoding things, decoding. Secret codes and stuff. So. What are they using? The electronic version of this. What are these? 没有人知道吗？真空管 Yes, correct. These are vacuum tubes. Correct. Oh, sorry. I don't know if you guys are into technology histories or not, but they used to have these vacuum tube computers. They could also do computing because it's like light bulb. We're now turning into LED lighting. It's the same thing. It's like a light bulb. You do the calculation, you do the control of electron beams through a vacuum tube, and there's a gate, there's an anode, there's a cathode and anode. So you have electron emission through these two electrodes, and then there's a gate controlling the current flow. So basically what a transistor does, or vacuum tube does, is that you want to be, in an electronic system, what you want is actually you want a third module to control whether the current flows or not. It's like a switch. So the basic idea of a computer is a switch. The logic 0 or 1 is a switch. So you can also use vacuum tube to make a computer. So they used to have like a computer with the power of like very low-end computer. So it would take up a huge big room, and it would take up a power plant to fire up this computer because it takes up so much power. So the problem with vacuum tube is that it's the same as light bulb. The problem with light bulb is what? It's power. The size is large, of course, and then it requires high power. And then the lifetime is limited because they burn out easily, because a large amount of power going through these devices, your electrodes burns out easily. Therefore, they need to go in and change all the light bulbs constantly. Okay? So then people start to think about, why would I want to do the switch through vacuum tube? I want to make a transistor we call the solid state transistors. So now you don't want it to be in vacuum, you want it to be in solid state. So they start looking at semiconductors. So they start looking at semiconductors. So the most advanced research that was done in those times are from Bell Lab at the East Coast of the United States. And they start pursuing the solution because vacuum tube is not a very good, reliable element for that. So people start making solid-state transistors. So the first solid-state transistors are made in Bell Lab in 1940s, and it got a Nobel Prize. This is the first Nobel Prize going into engineering field. And three of the inventors got Nobel Prize on developing or inventing this transistor, solid-state transistors. So this is a very poor transistor. You can see that it requires large electrodes, and then it's only a single transistor. So they successfully made the transistors. And does anyone know that what are the semiconductor used in this type of transistor, the first transistor? Do you know? 有人知道吗? What's the material used in making this transistor? Look up your periodic table on correct. It's not on silicon, it's on germanium. Germanium, 没错, it's on germanium. The reason why most of the early stages, in the early stage of semiconductor technology development, people use germanium-based devices a lot. The main reason is because it's easier to refine, because germanium melts at around 900 degrees C. So you want to make pure. The purification of material is very important in making semiconductor devices. So people start with germanium because it is one row downwards. So it's actually less, less robust material. So you can actually purify it much easier. And then we elevated into silicon, and people are looking to what, if you go up, what's the next? Periodic table. Yeah, so then you start with something called silicon carbide. silicon carbide will be the next thing to go for power devices. So people are working on silicon carbide. So you want to combine to make it more robust for handling much more power. But that's the way it goes. But now people come into germanium as well for other purposes. If you're interested, come to my class in solid-state devices. Okay? So then, so as I said, you start with a single element. You can make a simple transistor. So that's a big step in moving from vacuum tube into a solid-state devices. You make the devices more robust, less power craving, and then make it more reliable. And then what people think about is that I don't know if you've taken courses of making circuitry on the 面包板那种的 board. Yes? So what you do is that you place single elements or some IC elements, and then you do the wiring through a wire, right? So you want to connect a node in the circuit. For example, if I have a resistor and I make a capacitor, so I have these two terminals. Sorry. I have two terminals coming from these two, say just a passive component. So this is a capacitor, so I have this terminal and this terminal. And I want to wire them together. Okay, so when you do it on the board, what you do is just to place a wire. Okay? So, but if you want to do it, we call it integrated, meaning that when you make the devices, you want to make sure the connection is being done. So think about what you need to do is that you want to make terminal 1 and terminal 2 shorted. It's simply a short. So what do you actually need of making a wire? What is essential in a wire? Think about it. What are the layers required? If you want to make it an integrated circuit, you then need two elements to make a wire. Think about a wire. What is a wire? So I want to wire these two nodes together. What are the key elements in a wire? You think about a wire, there's the metal, and there's the what? Plastic, right? So the wire is for shorting, the plastic is for what? Correct. So what you actually need to make an integrated circuit, aside from these devices, is two key important components. Is called we call the interconnect, which is the metal wire. You want to metal wire with, we call the interconnect when you make it an IC. And then you need isolation. So that's typically done with dielectric layer. So these are the two components. You want to make sure that it does not short everywhere. You only short it from point 1 to point 2. So think about a wire. What you need to make in order to make these circuits onto the integrated circuit is by providing technology of metal and isolation. So if you ever think about integrated circuit, the back-end process, we call the back-end process, there's only two components. One is wire, metal. The other is insulation. So you make sure that these wires doesn't touch each other. So that's how they make integrated circuits. And both of them invented at very closely time frame. So one is Jack Kilby. He made the integrated circuit, and the other is Robert Noyce. They're considered the inventor of integrated circuits. But I believe Jack Kilby won the Nobel Prize. I always ask this question. I don't know if anyone know the answer. Does anyone know why Robert Noyce didn't get it? What do you think? Because he died earlier than 2000. So people were joking that if you want to get a Nobel Prize in engineering, because the impact of the invention will take a long time, so you need to make sure that you're healthy and live a long life. I think maybe Robert Noyce is a smoker or something. Okay, anyway. Okay, so let's take a break for 10 minutes, and then we'll come back and we're gonna wrap up this introduction part. Let's continue our discussion. We'll talk about, being healthy so that you can get the Nobel Prize. So the next, so if you look at the progress in technology, the first, mostly people consider Robert Noyce's implementation of integrated circuit more realistic or more closer to what has been done in today's integrated circuit. Therefore, if you consider this 6 transistor, they have combining 6 transistor on the same substrate, we call it mostly semiconductor substrates, and then you can then now build we call it the first version of integrated circuit, consists, as I said, the 6 transistors. Nowadays, any of the transistors you take up will have millions or billions of transistors. So if you look at just a simple 4-core CPU, it will consist billions of transistors. So there's multifolds of progress in this, the compactness and also the density of transistors in a circuit is overwhelming. So, this just to show you how much the progress has been done on transistors. So the next thing we're going to talk about are what are the key elements in the circuit. We have already talked about the passive components, of course, are typically referred to the resistors, capacitors, and inductor. So when you inject current into for example, if I inject current into a resistors, where does this power go? It turns into what? Where does the injected power go if you inject a current? Apply a voltage, and there is a corresponding current, right? So apply a voltage, and then therefore I'm injecting the system with a power of IV, right? For stickers, come on. Yes. Yes, correct. So what happens in capacitors? If I charge up a capacitance, it will then build up, there will be Q plus and Q minus on a parallel plate capacitance. So where does the energy go? The electric field, correct? They actually store in electric field format. So in here, when you inject a current, it will then be stored in a correct magnetic force. So your energy doesn't go away. It will then, if you're using an LC oscillator, it will then transfer from electric form into magnetic form, and then magnetic energy, electron energy, and then it oscillates. And if there's parasitic resistors, and then will dissipate a little bit over in the heat. So if you have a perfect LC oscillator, then it will just transfer the energy between electronic energy into magnetic energy, and then it will transfer between the two. So it will oscillate forever. But in the real world, of course, there's a resistance, parasitic resistance. It will then use up, dissipate, and heat a little bit. So these are the passive components. If you look at passive component, what typically being done, if you combining passive components, they will actually, if you look at in a signal way, if you look at the signal amplitude or signal power, it will always decay. Either it will either maintain, as I said, if you have an ideal LC oscillator, it will actually maintain the level, or either it will decay because there's resistive elements. So either the power decayed eventually, or the signal power actually at the end will be lower than its original level. So it does not have any amplification effect if you simply use passive component to build a circuit. That means that my signal here, for example, in this system, there is a microphone. this microphone picks up on my voice, and then you hear it out on the speaker. Okay, so through the system, my signal, the signal of my voice is being amplified. So if you want to complete the system of amplifying my signal, making my signal more powerful, meaning I'm giving out a little voice, I'm keeping it very low, but still the speaker will give out, it will reflect my signal, but at a much higher power, then it will require active component. So these are the two active components we're going to address. One is called the MOSFET, the other is called the bipolar junction transistor. So anyone know what it stands for? Anyone want to try? 单载子. Yes, yes, correct. But that's I'm just trying to say, does it know what the words means? M stands for what? Does anyone know? 有人知道吗？有人知道这个 MOSFET stands for what? 赶快查，赶快查。O 是都没好，那你可以选，你要选 O 可以 O 对。Metal. Yes, someone got it from the computer. Okay, so what it consists of, what I want to talk about is, this is a type of devices. MOS is for structure. So MOS stands for the structure part. If you're interested, you look it up. Okay, I'm not going to talk about the details. So it's the metal oxide semiconductor is referring to the structure. And FET stands for how it functions. So FET, someone to say what it means? F is field effect. So what it does is that it's counting on electric field. So this is how it works. So the first three is the structure, and the second part is to tell you how it functions. It functions through electric field transposing through the dielectric and induce a channel. So we're going to talk about that when we talk about devices. But these things reflect something. So anytime you look at a word or look at an acronym, you want to make sure that you understand what the point is trying to convey, so you get the sense of what it means, or also the function or the difference in devices. So for the next part, it's only 3 words. Anyone want to guess? Bipolar junction, correct. So T is for transistor. Everything is for transistor. But it means that it goes both directions, so it's bipolar. Junction is construct of junctions. So this simply means PN junctions. So we have 2 junctions. So this is the symbol for the device. We're going to talk about that, of course, later in classes as well. Okay? So it's good to get the... So as I said, if you're trying to build a circuit on the board, you go get the resistor, remember like the smaller thing, the resistor, the capacitors, you can go buy those. These are, on the left, are the resistors. When you build a circuit, external discrete circuits, you can get these discrete passive components. These are inductors, these are capacitors, and these are resistors. You can go buy those. And then because you can actually redo them using integrated technology as well. Remember, integrated circuit, the key of making integrated circuit is to make transistors. So based on transistors, and there's only, let me say this. In integrated circuit technology, in IC, there's only 2 components. One is to make transistors. What type of transistor will depend on the technology itself. So one is that you have transistors. The next thing is that you have interconnects. Interconnect layers. So the purpose of IC technology or the buildup of these is mainly to make transistors and make the wiring of connecting these transistors. But if you wanted to incorporate passive components, for example, resistors, inductors, capacitors, you can also do that, but without additional processes. The best thing is that you don't want to make your process more complicated. You look at what you have and use them to deliver the same electrical characteristic. So these wires, this is called you can see that structure like this. You can see that it goes like this. The blue is just revealing this is a resistor using a long line. So we know that resistors we know that it depends on what? It's proportional to proportional to length. Inverse proportional to what? Resistivity of the material. So this is resistivity proportional to length. Inverse proportional to what? So area, correct. Cross-sectional area. So if you look at this, this is the top view of the device. If I cut it here, and have a look at this cross-section, AA prom, it will look something like this. It will be a wire with the width of W. And these are made with wires, so it's mostly we call the thin film transistor. So this is the, sorry, I don't know what happened. And it suffered one class. It's called a thin film. So it's made by thin film, a long, very long thin film transistor. So this is thin film, meaning that this is the width of the transistor here. This is the width, W. And the thickness of the film will then be a fixed level because we know that they're always the same thickness. There's a thickness. T is the thickness. So if you ever make resistors in integrated circuit, they will not give you a resistivity. They will give you something called a shear resistance. Let me show you what it means. So this is resistivity. Your cross-sectional area will become what? What is A? Will then be W times what? Your cross-sectional area is this, right? The current is flowing this direction. So your cross-sectional area is W times T. And because T is fixed on the film, so this is referred to as R squared, or we call the shear resistance. So if you ever want to make resistors in integrated circuits, they will give you the number. If you want to use this particular film, it will give you the resistivity divided by its thickness, because thickness are fixed in a film. This is referred to as the shear resistance. So then you can determine your overall resistance by simply drawing the layout, because what the designer can control is the top view, the layout of the circuit, layout of the resistor. So you can plan how long the wire is going to go and how wide it is. You can determine W and L, but you cannot determine resistivity and thickness because there's a technology base. So for example, if you're going to tape out your circuit at a foundry company, for example, UMC or TSMC, they will give you shear resistance and you will determine the length and the width of your structure. Okay? And on the right, this is a parallel plate capacitance. So parallel plate is that you have mainly a top electrode and a bottom electrode. And so the capacitance will be area times permittivity divided by thickness of the film. Let's say this is TD. Thickness between the film will then give you the capacitance. So what can be controlled in most of the designer's domain is area. You can design the area, and typically the dielectric constant or dielectric permittivity of the material is given depending on what layer you use, and then the thickness are typically given. So for design purposes, you can only design the area of your capacitors. And we need to realize that if you ever break open your, not iPhone, but some computer, you will actually see there's passive component, especially inductors and capacitors. The reason why, even though in an integrated circuit, even though we have the capability of making integrated inductors and capacitors, mostly they are not very ideal, meaning that it would take a lot of area to actually make some substantially large capacitors. And also, capacitors is a very expensive thing because it takes up a lot of area. If you want to make, I don't know if you guys know the level of capacitance being made in per unit area in integrated circuit. Does anyone know the level of capacitance typically being used in a circuit, especially integrated circuit? In microfarad or nanofarad? Does everyone knows the unit, right? So you know there's micro, that's 10 to the minus 6, right? So what's next? Let's use dimension, okay? Use dimension so you get a better sense. So then you get this. Or current, you use current. Current's probably get a sense. Sorry. Let's use current. So let's say in a transistor, does anyone know that the transistor current, what is the typical transistor current level? In an integrated circuit, for example, in a MOSFET. ID, okay. What is the range of the current typically? Like in milliamp or microamp or nanoamp? So we start with, let's just line. What did I do? Okay. So you start with, everyone knows what micro is, minus 10 to the 6, right? 有人知道电锅用多少电吗？ You just get a scale as to what are the current levels or what are the power level. 没有人家回去看一下你家电锅。Current 多少安培？对，差不多10安培左右。10 amp. So for heating up things, you need about 10 amp. So for micro circuits, it will be much lower than that. So what is the scale? Just get a sense. So let me give you a reference. So this is typically in 1 milliamp to maybe 100. When you turn on, it's micro. 100 microamp. When you turn on the transistor, so these are the transistor current level. So that's microamp, and then you will then have nanoamp. Nanoamps 10 to the, how much? Minus 9, right, nanoamp. And then you have picoamp. That's 10 to the minus, how much? 12, correct. And then what's the next? 10 to the minus 15? Does anyone know what it is? Femto, correct. And then there's the minus 18. This is very rarely used, but we're not into that level. But typically, you would then encounter devices operating in femto. We're going to talk about that a little bit in your detectors. So this is actual A. Okay? But anyway, just to give you a scale as to what are the components in, or what type of level it will deliver. So for capacitance, we'll talk about capacitance. Capacitance is typically, if you consider area micron square, this is probably in maybe 10 to 100 femtofarad per micron square. Now let's just say that its capacitance density is very low. Therefore, if you want to make large capacitance, you need to resort to external components. That is why in some of the circuit you will still see a big tank of capacitance, because you need that large capacitance for power reserve, or you wanted to do like rectifying circuits that has a lower frequency, then you need large capacitance that it's not cost effective to make them in integrated circuits. Okay, so the last one is the microcode. I probably need to move along or else. Okay, so this is just to show you what a discrete component versus integrated version look like. So on the left, if you want to go to buy a transistor, this is a discrete transistor. So you might go get a discrete BJT, for example. So it comes with 3 pins. Okay, so it's a package and with 3 terminals externally expanded. But if you want to make these into interconnect itself, how do you make those? You made this by drawing a blueprint. So on the right, this is called a layout of circuits. In architectural term, it's a blueprint. You have the blueprint, you deliver this blueprint to the manufacturer. So it's like if you're an architect, you make a blueprint and you give it to the construction company. So they make the house, they make the building for you. So this is the same thing, is that you give the layout and then they will give you this. This is the cross-section, we call the cross-sectional view. Of a circuit. So you can see that, I don't know if you actually can see this, but mostly what you can see, the bright part are metals, and the dark parts are isolation. So you actually see mostly the wiring on top. The circuit is underneath here. You can barely see this. So these are the semiconductor. So we call the semiconductor substrate underneath. Substrate. So these are, let's say, silicon substrate underneath. On top are we call the interconnect layers. So these layers are simply to do the wiring. So there's more complicated wiring because of a lot more transistors. Therefore, it's more complicated wiring. You can see the wire going horizontal or vertical directions to make your circuits functional. So these are, as I said, these are metals. The bright parts are metals. So you see these metals. And these are insulator, dielectric. Okay? So this is the cross-sectional distribution illustration of how the circuit look like. We're going to talk about that. You can just keep in mind, we're going to discuss this more. This is a inverter. So if you look at the cross-section, after this course, I expect you to see the inverter itself and how to function as an inverter. So if you've ever seen a silicon, has everyone seen a silicon wafer before? 有看过的人举手，都没看过。我今天有I got some. Nowadays, this is old technology. This is 6-inch wafer. When I start making, I remember when I started doing experiments on the micro lab, we use 4-inch wafers. It's a little bit smaller. So this is a 6-inch wafer. I don't know if you So pass around. Anyone want to see it? Close up. So that's a 6-inch wafer. And nowadays, 6-inch are not that popular because it's not as cost effective. So you move on to 8-inch and 12-inch. So 12-inch wafer is like a plate, like a dinner plate. 我不知道大家看过 dinner plate， 它就是 12-inch， 差不多这么大，比较重一点。So this is nowadays, I think, not necessarily moving to 18 inches because it's either harder to handle, but the main mass production or the sweet spot now lands at 12-inch wafers. So you can look at all of these. These are we call it, you actually cut this off. This is like a die. This is a field, and you cut it out, and then we make it into, where is it? I lost my chips. I bought some chips. Oh, here. Then you package them and then turn into chips. So these are the chips. I don't know if anyone wants to see. And then you mount it onto a board. And this will be, you mounted the chip onto this board. Okay? Okay, so what is next for integrated circuit progress? It has been moved along, as I said. There's billion of transistor integrated circuits. And people are trying to these devices are making, we call it 2D circuits, meaning that all your transistors and at the surface of your wafer. And then people are trying to stack these transistors up. We call the 3D IC. So if you want to stack them up, you can stack 3 transistors, 3 layers of IC together, or you want to make it sequentially. Nowadays, people think that advanced, I typically refer to as advanced packaging systems. To stack these layers together is probably the better way to go. If you want to build them sequentially, it will be less cost effective to do that. So in most of the engineering problems, we're not, one of the things I want you to consider is that you're dealing with cost issues, meaning that which of the technology is more cost efficient. It will be a very significant consideration when you're doing engineering, or when you're solving engineering problems. So what is the solution will become less costly or become more popular, or I should say, will depend on whether it's being made when cost is considered. So it's not just the performance side, it will always be the cost side in your design consideration. Okay? So the next thing we're going to move on. So I thought a little bit on IC history. I talked too much. But anyway, so we're going to move back into the chapter 1 discussion on the book, which is we're going to talk about what are the key components in your phone. So you think about your phone, there's two main purposes of your cellular phone. One is to communicate. Communicate meaning that it will, if I call you to make a phone call, for example. So if I call you, then what are the electrical signal pathway and what are the key components in this signal pathway? So one of the key modules in your cell phone is we call the transceiver. Transceiver is the transmitter plus receiver. It's called a transceiver. So there's 2 modules. One is that it will pick up my voice. Microphone will pick. There's a microphone in my phone will pick up my voice, and then it will then do something in the black box, right? And then it will then drive the signal, whatever I said, drive it into a signal. And then, what is this? Does anyone know what that means? It's an antenna. You have a built-in antenna. No, it's not ADC. It's an antenna. the ADC is within, it's not sorry. If you're not doing digital, nowadays it's all digital, but I'm just saying, if I'm just trying to amplify, transmit my voice out, I drive it out into antenna. So the antenna would then drive the signal out. So what it has to come in is that it would then taking my voice, and then it will then do the amplification. It has to amplify, and then it has to shift the band, called the because my voice is in, you know, the frequency of a voice, frequency of a speech, the speech voice. Does anyone know? 讲话声频的频率是多少？没有唱歌，没有啦，唱歌。So it's a very low frequency signal. My voice is a very low frequency signal, but the transmitted frequency of the cell phone is what? Gigahertz, right? 现在已经讲5G嘛，5G 就是 gigahertz. So this signal has to be driving in gigahertz. But what I'm been talking, this signal is the signal coming in is in kHz, maybe 20 kHz if I'm not singing. So it's within kHz, and then you have to, what we call the mixer. You want to blend it into, modulate it into high frequency, and then drive it out. So through the system, there's a lot of electric circuits allow this, my voice, to turn into a wireless signal which being modulated into gigahertz, and then drive it in, driver circuit is very important. We call it power amplifier. Because your antenna is a large thing, you want to make sure that it oscillates and takes out a lot of power. So driving is also very important. Aside from transmitting my voice, it has to hear your voice. If I'm calling you, your voice is coming through the station, and then the station will then emit this same signal, gigahertz, and then you want to, we want to transform back into voice band. So you want to do it to a voice band signal. And then you also need to drive the speaker, because the sound, there's a speaker inside your phone, and make the speaker oscillate in order to hear your voice. So that's the whole thing. Inside, there's a lot of signals, and the signal needs to be amplified in order to transmit long distance into the station. And then the receiver receives signal which is very small, which is millivolt. And you need to amplify that, make sure that it's being taken care, and you want to amplify it and turn into a voice band signal, and then drive it out to the speaker in order for me to hear it. Okay? So in all the system there, the signal amplification or signal processing is very important. How does it transform a voice signal into electrical signals? And then once it turns into electric signal, it has to modulate into different bands for different type of processing. Okay? The other thing, another commonly seen electronic system, which is called the digital camera. Everyone has a camera in your phone, maybe 3. Okay, I only got 1. I got 2. But I bet someone got the 3-eye big camera thing. So the camera, if you think about a camera, I always talk about million pixels. You start with 5 million pixels, meaning that each of the pixel, there's an amplifier. You have amplifier within each of the pixel. So if you look at a camera, it's very amazing. Each of the pixel is actually constructed of a detector. So this is, each of the pixel has a detector. This is the detector detecting the light. So you see all your pictures come with these detectors. You start with the detectors, and then you would then have the amplifier. Each of them has an amplifier. That means that in this such small little chip, a camera chip, it will have millions of amplifiers. So you want to make it very small, because you want, how do you how do you design? If I'm designing the amplifier without constraint, I'm only making 1 or 2 in the whole system, I could make it as I like. But if you're making millions of transistors, millions of amplifiers, that's a different design constraint. So I'm also teaching, I'm making the advertisement, but I'm also teaching CMOS mini sensors courses in graduate school. So if you're interested. Anyway, so each one of these sensors combined with the amplifier. So you need to know what is the purpose of this amplifier. The amplifier has to modulate this, to contain the signal and then drive it out into the signal path. I have millions of them. It cannot come out together. It has to come in sequence. So you have to control them through the switches. You have to amplify them, contain them, and make sure that it reflects whatever image, whatever intensity is received. Therefore, there's a lot of signal processing, amplification, and signal processing of these type of signals, your imaging signals, okay? So there's millions of them with your small cameras, okay? So the last two things I want to talk about is what are the two types of signal you typically face in electronic system. One is referred to as the analog signal. The analog signal is typically, the main idea of analog circuit, analog signal is that it's continuous, it has continuous value in continuous time frame. Meaning that if I'm referring to a signal V output, whatever, it's continuous in time, and it can be at any value. That's called a continuous signal. So this VT is continuous and it changes with times. So it's continuous, such as my voice. It will be up and down. It will be continuous. The light in the environment, all kinds of music format, waveform, they are all in analog format. In natural world, most of the signals we encounter are continuous. So these continuous signals, then you need to process this. For example, I'm making a sound here, and then this will be a continuous signal. I'm continuous giving out voice signals. But this signal will then will subject to a lot of problems in the propagation of the signals, meaning that if I'm having this is my original signal, this is my original singing, but if there's a voice, there's a noise in the system, what happens is that you will actually hear something else. So if you hear something else that's coming from interference from the environment, it may be a low noise vibration coming from the building, for example. It's coming into part of my signal, or in the electronic system, there's this 60 hertz power noise into the system. It will be very hard for an analog system to identify whether my voice is shaking or whether the signal, there's a noise in the component. It might be I'm shaking, my voice is shaking, or I'm speaking in the right format, but there's an underground shaking. So it's impossible for us to differentiate whether the noise is part of the signal or not. So the problem with analog system is that it's very hard to identify noise in a signal. So what we actually want is that we want to, for example, if I receive this particular signal, I want to amplify it. So if I amplify this signal, I time it to an amplification factor, what then becomes AOVT plus AOVN. Let's say this is noise. So both of them are being amplified because you can't tell. You assume that the shivering is part of my signal, but you can't tell. So you have to amplify both of them. So that's the problem of an analog circuit, is that in electronic systems, you might you might not be able to differentiate them. Therefore, there's no way to treat them. Of course, there's some ways of dealing with fundamental or input noise for differential design, that sort of thing, but to a limit. So in order to clean up the system, clean up the electronic system, most of the electronic system turn into digital system. What do you mean? What we mean by digital system is that I particularly assign acceptable levels, meaning that only finite numbers of values are, I only recognize these. So if you're out of the ordinary of steps, then I consider that as a noise. So for example, we're most familiar with the binary system, which you only have 1 and 0. 1 and zeros. So there's basically only 2 levels. So I'm only injecting 1 and 0, only the highest VDD and the lowest 0, only the 2 type of signals being input into the system. So I'm expecting my output should be either 1 or 0. So for example, this is the injected signal, which is 0 and 1. In terms of level, it will be 0 and VDD. So VDD is the highest level in the system. So you will have, for example, if I have a 3-volt system, that will be 0 and 3 volt. I only recognize these 2 levels. So if you're shaking within the tolerance of close to 0, I consider it as 0. Therefore, this noise, I can know that these are noise. I can tolerate noise because I be able to recognize if it's within, for example, my target is 3 volt. If it's 2.7 to 3.3, I consider it as 1. So I give it a tolerance. If it's within that, it will become 1 or become 0. Therefore, any of the noise injected into the system will not be recognized. It will be eliminated because I will not recognize them as part of the signal. My signal is only designed in 0 and 1 level. That is why the digital system becomes so robust, is because I could differentiate signal from noise. I turn everything digital, therefore I only recognize particular levels. Anything arbitrary within the 2 are unacceptable, so I assume that it's noise. Okay? So that we call it, this is one of the key components that in design is called robustness. We call it robustness, meaning that if you build a building, how do you test robustness? You give it an earthquake and it will not fall down. So that's the same thing. If I'm putting this system into a noisy environment, it will still give me a true signal, meaning that it's robust toward noise. If I give it a harsh condition, meaning that in high heat, it will still deliver the expected performance, then it's a robust system. So you want to make your design robust. So there's certain ways of making your design more robust and keep its performance even in a harsh environment. That's called robustness. So that is why most of the electronic systems are surrounded by, so if you look at electronic system nowadays, it will be a digital core. You want to make everything digital, so you will have a digital, we call it digital core. And then you will then have something called the ADC, analog to digital conversion, and then the outer world to the environment. Whatever signal coming in, then you will then have some analog component to pre-processing the signal. So the analog will be the interfacing with the natural world, because natural signals are analog. You have to deal with them. Once you pre-treat it, do some pre-treatment, and then sample, and then dump it into digital system to further processing, calculation, manipulation, everything other than pure computation, it will be done in a digital core. Okay? How many more pages? Okay. Okay, last one. So let's look at an amplifier design. As I said, in this course, we'll limit ourselves in the design mostly on amplification, meaning that what is an amplifier? Basically, what it does is that if I give you a signal, I expect the amplifier, for example, from the transmitter, from the receiver, I receive a very tiny, small signal of your voice, looking something like this. So this is probably 1 millivolt. It's very small. And it's very hard for me to do conversion, ADC conversion, because the signal itself is too low. So I want to make an amplification first, pre-amplification, pre-treatment of the circuit. So then this voice will be amplified. And then what I expect is that it will look something like this. Right? And then this is time. This is magnitude. So this will be 1 millivolt, and then the magnitude of this signal will then amplify by 1,000, become 1 volt. So this will then give me we call it voltage gain. The voltage gain is defined as V out, V in. So in that case, if I draw you this plot, you should be able to identify that the voltage gain of this circuit is 1,000. And if I want to, typically when we discuss amplify gain, there's another unit that's typically being used. It's called dB. Does anyone know what that means? So how much dB? It's 20. Well, so this will be 60 dB. Okay? So it would then give you a 60 dB gain in amplification. So once the signal is being amplified, what are the other considerations other than giving your gain? The other is power. Let's talk about power. So power will be the current. As I said, you want to stand at a particular point. It would then require a certain amount of, we call it DC bias current. So then, first of all, your gain is given. And then the other thing we consider is power. So what is the cost of running this system of bias current? And the last thing is called the speed. How fast can it respond? To look at speed, if you're looking at digital circuits, how much can it switch from 0 to 1? But for analog circuit, it will then determine by your bandwidth. So what determine the bandwidth of a circuit? We need to look at the next slide, which is the frequency response. So this is the frequency response on the high frequency. What it does is that it draws the gain, voltage gain. It's not a constant versus frequency. So if my signal frequency changes, what is frequency? Frequency is this. This is my period t. So the signal frequency is 1 over t, okay? Okay, if I'm running a faster frequency, I know I should let you go, but give me 2 minutes, sorry. So you'll see that at low frequency, you would typically remain at a high gain. For example, we get a 60 dB here at low frequency. And then it will drop all the way down to 0 dB. Do you know what 0 dB means? Gain equals to what? No. 0 dB is gain equals to 1. So above that, so this is typically referred to as my bandwidth. So before that, it will function as an amplifier. After that, it will not be an amplifier because the gain is less than 1. So this is 0 dB is gain as 1. So then you need to know that what your frequency response is in order to know what is the operation bandwidth of your signal, what are the appropriate signals that can be passed through the circuit and will not deteriorate, or it will not reflect whatever gain is being promised. Okay, last page. So this is a circuit. It's a classic design. This is like going to the cathedral. Okay, if you're a designer, architect, you go to the cathedral, you look at a beautiful building, and then how did they design it? What are the key points? And this is like classic design. So what I want you to aim at is that after this course, at the end of this course, if I give you this figure, you should be able to tell me what is what. For example, what is Q1 and Q2 does? What is the purpose of having Q1 and Q2? What is the purpose of, for example, Q16? Okay? What is the purpose of the output terminal, which Q15, Q21? So as I said, at the end of the final exam or near-end exams, I will then give you circuit examples, and you should be able to tell me what it does. What is the purpose of this particular structure? Okay?